I am Edmund Jorgenson. I will be co-presenting with my friend and colleague, the distinguished Matt Papi, who's back here. So we'll be switching back and forth. We are 2/3 of a small consultancy here in Boston called Hut 8 Labs. Our third, Dan Milstein, will be giving his fantastic talk about statistics in baseball immediately following this one. I recommend you stick around. It's a fantastic way to end the day before going into socialization. It's a lot of fun to talk. Our talk today is where data rubber meets the data road, some principles of data engineering. So that's kind of our names. Who are we? What's our history? Why are we giving this talk? Well, here's one way to explain it. You all saw Sri kind of showed about janitor work in data and asked who enjoyed janitor work in data, that kind of work. By my count, 4 hands went up in the entire room. 2 of those hands were mine and Matt's. Dan's was the third. So that's a very succinct version of who we are. We are 2 software engineers, not data scientists, who have really spent a lot of our careers working on data processing systems. So from the very small at startups that were just getting off the ground with analytics systems, up to places like TripAdvisor with their data warehouse and their commerce reconciliation systems, where the data was big and the mistakes were costly. Matt and I worked together on those kind of things, a bunch of stuff in between. And in our current lives at Hut 8 Labs, most of our gigs are kind of helping out companies that are dealing with data pipelines, data processing systems that are falling over or need to improve their operations, those kinds of things. So that's who we are. We've learned a lot of lessons about those systems, in other words. We've had a lot of experience with them. And frankly, a lot of those lessons we learned kind of the hard way. We have left a lot of blood, sweat, and tears on the playing field of data processing systems. And our goal today is to kind of distill those down to 6 principles. So what are 6 principles that you can kind of take and look at engineering data processing systems in the fervent hope and the fervent belief that this will translate into less blood, sweat, time, money, and so on for you in doing the engineering on these kind of systems that we think is unavoidable. We'll get a little bit into that shortly. And also, I think, can become more enjoyable. So one way to put my goal for this talk is I would hope that if the same crew is sitting here in a year and that question is asked again, how many people enjoy this work, more hands will go up. And that's what we're hoping for. So quickly, just in case we've had a little bit, I have a basic sense of this, but in case we've had a little bit of churn here, how many of you would say you're data scientists in your day-to-day lives? Okay, and how many would say I'm like more a software engineer who deals with data than a data scientist? Cool, so we got a bunch of you. Awesome. Data engineering. I've thrown this term around a couple times already, once in the title and then in one of the early slides. I haven't really defined what it means. I want to define what it means. I'm going to refer to an article you may have seen. You may have seen reference to as recently as Sri's talk. This is an article published this year by the New York Times with the title, "For Big Data Scientists, Janitor Work is Key Hurdle to Insights." There are many, many things that I love about this title and this article that we will be getting into. My favorite is janitor work in scare quotes. Now, if you have read this article, you understand that they don't mean that data scientists are having a hard time focusing because their offices are messy, because the janitors haven't cleaned up. They mean that there's janitorial work that goes along with data science. Getting the data, scraping it from websites that keep changing out from under you, grabbing it from FTP servers that are flaky and people who name files the wrong things, cleaning the data up because it's always a mess, reformatting it because it's never in the right format, finding the mistakes in it because there are always mistakes, footing it with other data that's describing the same things but that you can't link them up. They describe them differently. That's what we want to call data engineering and so on. That kind of thing and so on is what I want to call data engineering, all that janitorial work. And I want to say we could essentially have retitled this New York Times article as "Data Engineering is Totally Still a Thing." That's really what they're saying in this article. That stuff consumes a lot of people's time. I want to make a bold prediction here. The New York Times article ends on this very hopeful note. It essentially says if you are someone, a data scientist, who is suffering from this, suffering from doing this data janitorial work, this data engineering, don't worry. There are people developing software that's totally going to save you. It's going to do the data engineering for you. You will be freed from this. It's not going to be a problem. Here is my bold prediction. In 2114, there will be a New York Times article that says, for big data scientists, janitor work is key hurdle to insights. And it will still mean this, not the messiness of their office. Data engineering is with us to stay. Here's why I think this. You kind of consider what a data processing system does. At some level, it is taking a pile of data, and it is doing something to that pile of data, crunching it, and getting some insight, some analytics, some insight out of that data. I think that the optimism expressed in the New York Times article and kind of the hope that a lot of people have for the fact that this problem can be solved with software, these data engineering problems can be solved with products and software, is really emphasizing the pile part of this nature. Because software has proven to be fantastically effective at dealing with piles, right? There used to be piles of paper in every office in the world. Those have shrunk dramatically, in large part because of software. Piles of books by my bedstand are now this slim little Kindle with hardware and software giving me help. Software is great at dealing with piles. Well, yes, the reason I am pessimistic is because of what's on the right of that. This is not a pile of paper. This is a pile of data. And I believe that data is a very special thing and something that is not particularly amenable to these kind of software products helping you out. So I want to kind of define data very loosely, and we'll get into this a little bit later, as it's kind of a lossy representation of reality. And I believe that that's what causes these problems, is the nature of data as a lossy representation of reality, and of data processing systems, what those systems look like that process data. So here's 3 reasons, and we'll do kind of a BuzzFeed style, to move on from the New York Times thing. You will not believe these 3 reasons that data engineering is totally hard, valuable, and with us to stay. These are 3 characteristics of data processing systems that I think mean data engineering is with us for the long haul, as a human activity, not as a software product activity. 1, I'm only going to touch this briefly because this is actually one of our 6 principles. Matt will be going into this in greater depth. Data processing systems tend to grow up in this certain way, where they start as ad hoc exploration, somebody messing around with the data, looking at it, and so on, trying to gain that first insight, that first bite of insight. And from there, they kind of grow up into these systems that have to do that over and over again in an ongoing, repeatable way. There's a profound transformation that takes place between these 2 kinds of systems. And I think the fact that that transformation takes place, I think that's going to be a human activity, not a software activity. That's going to be data engineering for the foreseeable future. Second property of data processing systems that I think make them very hard, something that's going to be a human activity, data engineering for the foreseeable future, is what they do. They take in a bunch of numbers or other data, textual, whatever. They crunch it, and they produce something at the end that's like usually a bunch of numbers, right? Something that's supposed to give you insight. Are those numbers correct? So you fed a bunch of numbers in. It did its thing. You got a bunch of numbers out. Are those the right numbers? Well, they're numbers. Like, that's a good start, right? They're definitely numbers. How do you know if they're right? This is a real problem with data processing systems that I think is inherent in the nature of what they do. If you're designing a web page, you're implementing a web page, you're engineering it, you know what it's supposed to look like when you're done. And so you can see very quickly, you're like, oop, the sign up button is totally in the wrong place. I can fix this. I know right away that it's wrong. A data processing system is by its nature trying to give you insight into the data that you did not have before. It is trying to tell you something you did not know before. How do you check that against a kind of known good? It's hard. It means it's trying to tell you something you can't check by its nature. This makes it very difficult. Even worse, the third principle, an extension of this, is what you then do with that insight typically. Typically, you're not like taking that insight and doing nothing with it. You're making a decision based off of the results of your data processing system. Some form of analytics is going on. You're getting an answer. You're making a decision. Those decisions can be extremely expensive if you are wrong. And to give a short example, I'm going to give the story of Redacto Corp. That is not the real name of the company, although it was a real company. So Redacto Corp is totally free if any of you want it for your companies. This was a small startup started by some people that we knew. They were essentially a subscription business of a certain kind, and they did all the things they were supposed to do when they were setting up their business analytics. They were measuring all the right variables. They were measuring their churn of customers and how much it cost for them to acquire a customer and how much a customer was worth, and all that stuff, they were doing it. And they got some very sunny numbers out of the end of that processing. And on the strength of those numbers, they went and they raised a chunk of money. And then some ways down the path, they discovered that those numbers weren't being produced correctly. Those were not the right numbers. Those were not the truth of their business. The truth of their business was decidedly less sunny. Now, I want to be super clear. This was neither like a stupid mistake that they shouldn't have made. This is the kind of thing I've done 100 times, the kind of thing anyone working on these systems has done 100 times. And it was not at all with kind of mal-will. This was well-intentioned, decent, competent people who made a mistake in how they were processing this data. They made some decisions based on that data that were wrong. And partially as a result of that, Redacto Corp no longer exists. This happens all the time. This is inherent in the nature of data processing systems, that the decisions you make based on that data can be very expensive if they're wrong. And another thing that makes data engineering so important, and what we're going to be talking about. So, last word before I turn this over to Matt Papi for our first principle. What do we mean by principle? These are not rules. These are not boxes to be checked. I want to define a principle for the purposes of this talk as something to value in a system, a way to think about a data engineering system, rather than a box to check or a thou shalt, thou shalt, thou shalt. So speaking of which, I will turn over the mic to my colleague, Matt Papi.
Thanks, Edmund. So hey, I'm Matt, and I'm going to be presenting to you a few of the principles that we're going to talk about today, starting with number one, which is think in pipelines. So what is a pipeline? You can think of a pipeline as a series of connected steps where the inputs and the outputs are well defined, where the data that's produced by one of these steps is going to be passed into the next step as its input. So I have an example of one here. Let's say that I run a website, and I've got a bunch of weblogs, and I want to build a usage report to see who's using my site. So I'm going to build a little pipeline for that. And it's got 3 steps. So first, I'm going to parse those weblogs. I'm going to read them from disk. I'm going to normalize them, extract little bits of information that I think would be useful. And I'm going to write those out to the next step, which is going to filter out crawlers. So say I don't want Googlebot in there, messing up my numbers for my usage report. I'm going to filter those out. And I'm going to write anything that's not a crawler out to the last step, which is going to aggregate those things and roll up some numbers and print out a nice table of usage. So that's a pipeline example. Written another way, how many people here are familiar with this kind of way of writing a pipeline? So if you're not, this is a shell pipeline, so like in a Unix-based operating system, where the steps here are actually programs, and they're connected by pipes. So the data that's written out by one is immediately fed into the next one. And if you are familiar with these, you might be thinking that this isn't really, in a large-scale data processing system, these maybe don't have a place. They're kind of a command line thing, shell scripting. But in fact, actually, in our experience, we built a lot of systems, processing various sizes of data. You'd be pretty hard-pressed not to find one of these, somewhere, maybe even kind of foundationally in the systems that we're building. So I'm actually going to contrast these here today with systems that you can think of programs that kind of process the data and modify it in place, kind of work on it all at once. So in my example here, maybe a program like this would be reading the data from disk and kind of filtering out the crawlers as it goes, maybe writing some data to a database table, reading it back out, kind of operating on it all at once. And so specifically, I'm going to talk about 2 benefits that pipelines have as an abstraction for data processing systems over the kind of modified in-place approach. So benefit number 1 is that pipelines are really easy to understand. So going back to my example, if I show you this pipeline, and it's 3 steps, I don't have to tell you kind of, you don't really need to know the implementation of how I'm filtering out crawlers. So I might be doing some substring matching or regular expressions or maybe some crazy machine learning thing or something. You don't have to know about that. You can just kind of look at that definition and you can see and kind of guess what those steps are doing and what the data that's flowing into and out of them might look like. So comparing that to kind of a modifying in place approach, to kind of understand what it does, you may not, you may have to kind of open it up, look at the implementation, maybe generate a call graph. So even like a well-architected one, it's not going to be quite as straightforward to tell what it does. And in our experience, as that kind of program tends to grow, it gets even harder and harder to kind of figure out how they work and sort of how the data is moving around. So that's benefit number one. Benefit number two is that it's easy to change the way that your pipeline behaves. So if you have these things set up as a series of steps, adding a new step, kind of moving the steps around, when you're in a situation where you may not know exactly what your pipeline is going to end up looking like, is a really powerful thing. So going back to my example, I've got this usage report, things are going really well, but kind of looking at sort of hits on a website is not quite good enough. I want to actually know about sessions. I want to kind of, see not just how many hits we have, but how long users are spending, how many pages they're hitting in that time, things like that. So with a pipeline, it's pretty easy. I add a new step, collapse sessions. It's going to kind of roll those things up, and it's going to give me sort of a bunch of information about kind of sessions in aggregate. And I may, I have to modify my usage report step a little bit to read in sessions rather than just hits. But for the most part, there's a clean kind of separation of where I'm collapsing those sessions and writing them out. In the case of a program that modifies the data in place, doing this might not be so easy. If we're kind of doing the filtering as we're reading the logs and kind of working on things in a bunch of different places, you may have to do a little bit more refactoring or that sort of thing to get this change in functionality to happen. So to recap, pipelines are great as an abstraction for data processing systems because they're easy to understand and they're easy to rearrange. Principle number two, data processing systems are born as scripts but must become software. So this may seem obvious, but I want to make a distinction here in the way that programmers tend to think about scripts versus software. So scripts you can think about as being sort of temporary programs, kind of one-off, a list of things that someone put together, steps they need to automate rather than having to run them by hand. And when I say scripting, I'm specifically not talking about scripting languages. It's possible to build software with scripting languages. We use Python all the time. We love it. It's great. I'm talking about things that are kind of temporary in nature. And software, on the other hand, is something that is more permanent. We tend to make investments in it to make it more robust. It has kind of a mini sort of ecosystem of supporting stuff. So it's things like this. With software, you've got tests. You've got a deploy process, version control, log files, monitoring, things like that. And I'm not saying that when you're building a data processing system and you're starting out, scripting is actually great. It's sort of exploratory, it's fast, it's not going to get in your way. If you don't know what you're building, you can kind of get something up and running quickly. You can start to understand the nature of your data and get a feel for what your pipeline is going to end up looking like. So I'm not talking about scripts as being bad, but if you've got scripts that kind of, you sort of worked on them, you've added a bunch of stuff to them, you're starting to lean on them really hard, and you're not making these kinds of investments, that can get a little kind of messy. So you start to hear things like this. If you're in that world, you'll hear people saying things like, well, yeah, the script that we use to run that report, it's only on this one machine, and there's only one person who knows how to run it, and they are terrified of having to edit it. So I'm actually going to refer to these now as the scripts that were just going to crash on your couch for a few nights, but a few months have gone by, and they're still there. So if you have one of these, how do you know? You may have a file name that looks like this. So how many people have seen something like this in a system they've worked on? It's .final, there's a date stamp in there. People have been kind of adding to it and moving it around and copying it. That's not great. So other things you might see in this world, file names that look like this. There's a .final, there's a .real. How do you know which one's being run? Maybe they're both being run. Not a great situation to be in. Hand editing config files in production. So you've got a cron job that kicks off your big data pipeline every Monday. And someone comes to you and says, hey, I have a question about the data that it produced. Can you go in there and try to figure this out for me? And you log into the machine that runs it, and the config file that you want to look at to kind of understand what it ran was modified on Tuesday. So the run was on Monday, the file was modified on the Tuesday. You really don't have a way to know kind of what the state of that thing was at the time that it ran. You don't have version control. So you're going to have to guess. Similar to that, one-off runs. So your system runs its thing every Monday, and someone says, hey, I have a question about that run from last Thursday. So you kind of, you sort of smile and nod and say, yeah, I'm going to look into it. And you're thinking to yourself, Thursday, that's, there was no run from Thursday. So you have to go and kind of figure out, who ran it, what did they run, what machine did they run it from. There's no way to kind of track that down. And finally, scripts that kind of only one person knows how to run, and they go out on vacation and something breaks and you have to fix it. You have to kind of get in there and dig around and try to figure out what they did. So you really don't want to be in this world. And we know, kind of as software engineers, we know that these things are costly. But I really want to emphasize that when you're working with a system that's processing data, and especially one that's kind of ongoing, you're running it repeatedly, these things are even more costly. You're going to be subjected to all kinds of new inputs. Every time your system runs, new types of data, new things coming in. And that's essentially a multiplier on the cost of all the maintenance that you'd have to do. So to recap, scripts are great when you're starting out building your pipeline. But if you treat them like software earlier, it means that later on, you'll be able to avoid a whole bunch of costly problems. So that's principle number 2.
Thank you, sir. Principle number 3, optimize the mean time of changes to your system. Making changes fast, in other words, for your system. I want to recap in a slightly more, bloodthirsty slide, I guess, a version of what Matt has just been talking about software versus scripts and so on, which is that your data processing system is software. It has all the nature of software as well as kind of the special things of being a data processing system. And here is one thing that we know to be true about software systems in production is that they have changes ongoing all the freaking time. So, you just delivered the first version of your software, you just got it into production, you're exhausted, it's just across the finish line. It's like you've got maybe 5 minutes before somebody comes up to you and asks you to make a quote-unquote small tweak, or before someone discovers the first bug that needs to be fixed, or before someone discovers the first new awesome thing that the software could do that it's not doing that will require a change. Your software is going to change all of the time. Your data processing software is going to change all of the time, your data processing systems. And there are things about data processing systems that make this even harder than it already is with normal software. And I want to get into those. So what do I mean by a change? Just to do very quickly the anatomy of a change. What am I talking about? The discovery, development, and deployment have gone on in a change. And so what I mean is discovery, someone has either found out your system is not behaving as it should, there's a bug, or they have a new feature request, they want to look at things in a new way. So either doing something it shouldn't or not doing something they would like it to, and they want that to change. So this is discovered. You have to develop that change, right, locally usually, and get the software to work the way that you want, and then you have to get it into production. So that's deployment. All 3 of these are problematic with normal software, extra problematic with data processing systems. Fast changes tend to equal happy people around you. So if you're responsible for one of these systems and the changes are going out quickly and they're going out well, your bosses tend to be happy, your coworkers tend to be happy, your customers tend to be happy. That's good. If, on the other hand, the changes are going out slowly, there are sad people around you, your customers and so on. They tend to just not have that spring in their step that they do when things are going out quickly. And in extreme situations, that can lead to them deciding that you are the cause of their sadness, and they would be a lot happier without you in their world. We want to avoid this. Like I said, all software has this nature of needing to be changed. All software is not easy to change without investment in making it easy to change. There's 2 kind of pieces of the recipe for fast changes that are especially difficult with data processing systems. And this is what I want to really hone in on. Number 1 is that it is almost always faster to do all three of these things, discovery, development, and deployment, locally rather than on other machines remotely. So if you're an engineer, you've got your laptop open now, perhaps you don't want another laptop. You don't want to be working on another machine because you've set it up just the way you want. You've got like 12,000 lines of Lisp in your Emacs file. You've got the tool chain just the way that you want. You've finally made Eclipse perform some things with some reasonable modicum of sanity. And that's how you want to develop. You're much faster that way. Network latency is a real thing. Logging onto other machines is there's actual hops that it's making. You're typing and nothing's happening. That slows you down. You're competing with other people on those machines. Those CPUs aren't all yours. You can't just unleash them to do what you want them to do. All of those things slow you down. So local is faster than remote for all three of kind of the pieces of a change. And local is harder than remote, even harder than usual with data processing systems. That's because they tend to involve specialized software that you might not have even installed on your laptop or your workstation. They tend to be dealing with large quantities of data that are kind of hard to deal with locally. They tend to have a lot of configuration. So unlike a web app where it's pointed at a database and go, there's all these things that have to be tuned to get it to work like production. All those things tend to slow you down. The second kind of property of data processing systems that makes these cycles slow is that there's this fundamental truth that you can't make a change in a software system any quicker than you're getting feedback from that system. The whole loop of a change, discovery, development, and deployment, is lower bounded by how quickly you're getting feedback from your system and from reality. So for a simple example, you can't fix a bug until you know that the bug is there, that there's an actual bug. And that tends to be slow with data processing systems because they tend to run for long amounts of time, unlike web apps where you see things right away, errors start spitting out. And sometimes they're a little bit even harder to discover than that, as we'll talk about. So that's the second kind of piece of this that's difficult. And I want to kind of just march now through the three pieces of the anatomy of a change with some questions you can ask yourself that are opportunities for investment in these areas. If the answer to any of these questions is no, it's an opportunity for investment to make local development and quicker feedback easier for your system, and therefore make the people around you happy and make yourself less probabilistically fired. Can I run on a subset of production data? So raise your hand if this has ever happened to you. There is a job that takes 12 hours to run, and everything looks fantastic. You go home, and it turns out that at hour 11, minute 59, the damn thing blew up. Has this ever happened to anyone? This has happened to me many, many times. When that happens, and I roll out a fix, I don't want to have to wait 12 hours to find out whether that fix worked or not. I want to be able to run on a subset of the same data so that it runs much quicker, and I can see quicker whether it's fixed or not. And I don't want to have to jump through a million hoops to do this, because that's slowing down my change cycle. And that's a terrible thing to do. Can I bring that data down for local use? Now, asterisk, in some worlds, this is illegal. If it's illegal in your world and you're dealing with people's genetic codes or whatever, this slide didn't exist. You didn't hear this here. I don't want to be involved in that trial. Can I, all other kinds of data, can I grab it? Can I grab it easily without jumping through hoops so that I can see how stuff performs on real data? Because most of the time it isn't illegal in most cases. And again, I'm going to be much faster dealing with this on my local machine than logging in and dealing with it where I'm terrified to because I might screw up the real stuff, et cetera. How about production logs for local exploration? Logs are text files. That's what's fantastic about them. I spend my life as an engineer dealing with text files. Believe me, I'm comfortable dealing with text files on my local machine and getting to the heart of what's happening in them. If I can bring logs down from production when there's been a problem or when something's going on and look at them with my own tool chain, it's much, much faster for me to figure out what's going on. We discover what's up, we develop it quicker, we deploy it quicker, changes go out quicker. Again, super easy since data processing systems tend to throw off massive logs. It's easy to not build this in. Take time and build this in. Invest in this if it's not something your system already allows easily. Are there tests and monitors in place for quick feedback? Again, if I break the build, do I find out quickly? Because there's automated tests in place. Monitors, we're going to do a whole section on monitoring. So I'll just mention that they're there for feedback. Development. There's really only one question for development that we've already talked about, which is, can I develop locally? This is the biggest thing. If you can't develop your system locally, you are slowing things down and costing your business money in ways that are invisible but massive. You are slowing down the change cycle. You are probabilistically fired. Deployment. Someday, I'd like to hear that from a boss. You're probabilistically fired, but on the other hand, you may have a bonus. Deployment. How do we make deployment faster in a data processing system? Or conversely, way of thinking of it, what's hard about deployment in a data processing system? Well, I've tried to stay away from things that are generally true of software as opposed to data processing systems in particular. But here's a question you always hear. I think it's even in like the Joel test, right? Can I deploy with a single command? You know, do I have to do I have to clear my schedule to deploy the thing because I'm going to be reading 16 out-of-date wiki pages that tell me to do this, this, and this? Or can I just be like, deploy, boom, and I know that it's done and that the scripts work? This is good for all software, but here's the kicker with data processing software. Can I do this while a data processing run is ongoing? Because those things tend to take hours. Remember, they tend to go for a long, long time. Unlike web software, where there's this amazingly fast request and response cycle, and you can come right in between a request and a response, and people don't even notice you've just deployed, and it's fantastic. Data processing systems, you're hour 15 into a 36-hour run, and you want to deploy something new. What are your options? Your options are wait until the end of that, which is not awesome, especially if there's another run coming right after that, right? You've got you're sitting there waiting to be caller number 43 in one of those summer sweepstakes, but instead you're waiting for the 4-minute window when the damn thing's not running so that you can deploy. That is not awesome. There are better uses of your time. Or number 2, you kill the thing. And you're like, no, all right, 15 hours in, well, we'll kill it and start it over. 15 hours gone. That sucks too. What you want is a system where you can deploy a change, the thing keeps going, the current one keeps going, and the next run will pick up your changes. This is non-trivial to engineer. It's an investment. It is eminently worth it. In conclusion, we optimize for mean time to changes by kind of 2 large areas of investment: support for local workflows and support for quick feedback loops. Speaking of those quick feedback loops, that sets us up nicely for Matt Papi and principle number 4.
So principle number 4 is that you should fail big whenever possible. Start this one off with a little quiz. So let's say you're working on a system that's processing some records, and the records always have one of 3 types. In your implementation, what do you do when a record is not one of those 3 types? So is it A? Well, yeah, OK, I know. I just said always one of those 3 types. But this is data we're talking about. There's always going to be a 4th type. You have to be ready for that. So do you log a warning and keep processing? Or do you stop the world and refuse to process another byte? So how many people think you log a warning and keep processing? How many people think it's stop the world, refuse to process another byte? So B people, I'm sorry. Actually, I gave you a little kind of snarky hint there on the slide. We'll come back to it later. It'll be great. The answer is actually always C. And there are 2 reasons for that. I'm going to explain them now. Reason number 1 is that it's always much harder to work backwards through your pipeline. So if you think back to my example where I was building a usage report and I had some user sessions that I was kind of rolling up. If I hand you one of those sessions and say, hey, tell me all the things that were used to kind of build this, that's going to be a lot harder. It's going to take you a lot longer than if I gave you the sort of initial pieces and said, hey, figure out what the session is that comes from this. You're going to have to do a bunch of kind of digging around, trying to find the original pieces of that were used to build that up from the input data. And you may not know if you got them all. There's going to be kind of a bunch of harder investigation that way. So it's always harder. It's much harder to work backwards than forwards. Reason number 2 is that failures get noticed and warnings don't. So this is store or drive. I'm sure you're all familiar with. There was a warning that someone didn't notice, and this is what happens. So if you're used to working kind of with software that's directly customer facing, you may have this instinct that you don't want your failures to get noticed. You want to fail gracefully. You don't want to put up 500 internal server error and stop that that user from doing their work. You want to try to recover basically. In the world of data processing, there's really 2 reasons why you don't want that. One is that with data processing systems, it's often possible to just rerun. So You don't always have that chance with, with the user in something directly customer-facing. But you can, with the data processing system, you can roll out a fix and you can kick it off again. So that's one reason. Reason number two is that you can, your data often can get corrupted. So if you try to recover and you're sort of passing that data that you sort of worked around further down the pipeline, you're increasing kind of the risk, the other opportunities for future steps to take that and kind of have their own failures and sort of kind of magnify that. So recovery in a data processing system is often a bad idea. So great news. You built the system, it hit a bad input, and it failed, and you didn't get a bad output. That's great. But still, at the end of the day, it failed. So what do you do about it now? One thing that you can do, and this is kind of the best, simplest, sort of correct option, is to try to fix the data upstream. So in my example with the usage report, let's say that these web logs that we're processing, once in a while, there's a log line that you hit that's just a timestamp and nothing else. So there's some misconfiguration somewhere, and it's a bad log line. Your system doesn't know how to handle that. If you can go into the web server configuration and fix that in the config so that those lines stop getting produced, that's ideal. That's simple. Other consumers of that data will thank you, and it's kind of the most correct option. If you can't do that, so let's say you don't have access to that web server config, you can, in your system, tolerate some amount of bad data. So let's say in a run, on any given night, your usage report runs through 10 million rows. And of those 10 million, 10 or 15 have this timestamp and nothing else. You can modify your pipeline to say, hey, any more than up to 50 rows, we're going to just kind of log it and move on. After we hit number 50, we're still going to fail. So that way, things kind of in your expectations, you're going to have 10 or 15 a night. If you have drastically more than that, you're still going to fail. And in this particular case, it's a usage report. 10 or 15 out of 10 million is not really going to throw off your numbers. You're going to be off by a small fraction of a percent. You're happy with that. So this is tolerating that is an option. And finally, if you've got a lot of bad data or things you can't really deal with, adding a transitional step. So if you built a pipeline, adding a new step that can modify that data, work around it, drop it on the floor, that's another option. So to go back to my example, this is a pipeline. So I've got this new step that I've inserted here after the filtering of the crawlers that's going to take those bad log lines or bad session information and not pass it on to the final step. And note that I've explicitly called this out here. I've named this remove bad sessions. I'm kind of drawing attention to the fact that this is a transitional thing. Other people that come in and want to look at this are going to see quickly that, hey, this is, they're working around some bad data here. So to recap, failing fast and loud is a good idea in a data processing system. It can stop problematic data from kind of working its way all the way through your pipeline and producing bad outputs. So that's principle number 4. Principle number 5 is adopt a forensic mindset. So what do I mean by that? What is forensic mindset? Well, before I get into that, I want to talk about some truths about data processing. So truth number 1, your software will have bugs. And this is true even if you have tests, even if you have stuff in place to try to prevent bugs, code review, et cetera, your software will still have bugs. Number 2, your software will be handed all kinds of bad inputs. So, other people's software will have bugs, see truth number 1. And that means the output of their systems that are being fed into yours, data may be bad or corrupt, and you're going to have to deal with those. Your hardware will catch fire. And sometimes I actually mean that literally. I have a great story, if you catch me after the talk, about a Hadoop cluster and an old network switch and a server room with a humidity problem. It's great. There actually were flames and smoke. It was a good time. And you are utterly powerless to stop these things. There's nothing you can do. So even if you have tests and you have version control and you've made all these investments, reality is going to find a way. It's going to find the one thing that you didn't protect against, and you're going to have problems. And finally, and this one's kind of special to data processing systems. The first bunch are kind of about software in general, but this one is that in a data processing system, you have a problem, and there's a bug, there's a failure that happens. As it moves through the rest of your pipeline, it's going to be transformed, and so it's going to come out the other end in some way that's barely recognizable, you may not notice that there's a problem. And even when you do, you're going to have to sort of work your way backwards through to figure out where it came from. Maybe it's a bunch of different things that combined in sort of a catastrophic way. So problems tend to show up far from where they're introduced. And what that means is that at the end of the day, when you've got a system that's up and running, you're going to be spending a lot of time investigating, understanding, answering people's questions about, hey, why does this data look funny? What's wrong here? That's going to really dominate the time that you're spending. So the forensic mindset is about building your system in such a way that it's really easy to fix and to understand and to fix these problems. So I'm going to let you guys in on a little secret. Edmund, cover your ears. I don't want to hear this. All of the other principles in this talk are actually just this one in disguise. So everything we've talked about so far, the one we're going to talk about next, are really about the forensic mindset. So if we look back at the ones we've seen so far, thinking in pipelines, it's about having easily understood steps, kind of clear boundaries between them. If something goes wrong, we can say, hey, it's probably this one step that's doing this one thing. Software, not scripts, is about having version control, so you have auditability. When something goes wrong, you can look and see this is exactly the state of what was running at this point in time. Mean time of change is so that once you've identified the problem, making the fix, testing it, rolling it out are as fast as possible. And loud failures are about responding to problems essentially right away, not giving them the opportunity to kind of move through the rest of your system and corrupt a bunch of data and cause problems like those. So in addition to the 4 principles we've presented so far, I have 3 specific tips from our experience for building better forensics into your pipelines, your data processing systems from the start. So tip number 1 is to lean on light-oriented text formats and tools as much as possible. So I'm going to explain this one with an example. Let's say you've got a whole bunch of data. Your customer is a bunch of shopping centers, and they have some files with information about users' purchases at various stores. So you've got some user info, some purchases, store ID, things like that. And you're building for them some intelligence about the people that are shopping there, kind of where they're from, what kinds of things they buy. And you get a request from support that says, hey, the zip code for this one user is 2141. That kind of thing look familiar to anybody? Anyone seen that? Someone's treating a zip code as an integer, great. So you need to track that down. And as it turns out, the data that I'm processing is actually a bunch of CSV files. So this is great. They're essentially plain text. We've got different things in different columns, but I can just open them up and read them. There's one line per record. And it's in a format that's really suitable to Unix command line tools with which I'm very familiar. So in this case, I've got that user ID. I'm going to grep through all the input data from this last run, and I'm going to see, kind of where does that user ID appear in the input data. So I do that, and I get a couple of hits, and great. Now I have something that I can take and start to kind of work my way forward through the pipeline. As you'll remember, it's much harder to go in reverse. So I can work my way forward to try to track this down. Tip number 2 is kind of related to this, building on that. Tag your data with source metadata. So what this means is that in your system, when you're reading data, in the sort of the first steps, and as you move through your pipeline, you want to add information about where the record came from. So specifically like file names, line numbers, add that to the record. And as you transform the data, as you join it, you merge it, you sort of move it around, you're going to update that metadata and basically say, here's where all of the pieces that were used to build this record came from. So in our example here, you can see that, hey, this record came out the other end with a bunch of stuff about where it was from. So I've got some stuff in the user file, some stuff in a file about stores. Presumably there was a join there where I had some store info from the stores that user was shopping at that I had to pull in. So it came out with all that information. And you'll actually notice too that this data is about 2/3 of the length of the whole line. This is resource intensive. It's gonna, you're gonna be moving a lot more data around. You're gonna be crunching a lot more data because of it. But it's totally worth it. And we actually have, in a real life system, we've done this, and it's been able to essentially cut the time that it's taken for us to identify problems and fix them down from on the order of like 1 to 3 days to 10 or 15 minutes. We essentially make them less costly. You can make them less costly if you build your system with.
Thank you, Matt. So our final principle today, principle number 6, monitor all the things. Once again, monitoring something that's important for any software system. Why is it especially important for a data processing system is what we really want to get at here. To get at this, I want to bring you all back to a moment in my life, a moment that I will never forget and that has shaped a lot of my kind of professional experience and attitude. And this was it. I was at TripAdvisor, fantastic company to learn about data at. And I had just started working with the data warehouse team, and I was tracking down my first problem in the data warehouse. And I was like, I know, I'll see where this bad result came from by going to look at the logs that were thrown off by the web application and other systems that were kind of brought in down there. And it was looking into the void, honestly, ladies and gentlemen. It was something I will never forget. I could not believe the crap. I could not even construct realistic scenarios by which the crap I was looking at had been produced. I was like, I do not understand what in our system that I've worked on the web app. How did it produce this? This can't be right. And I realized in this moment, this profound truth about data processing systems. You are downstream from a bunch of other software, human beings, systems, et cetera, that at best don't know you exist and don't care about you, and at worst are vaguely hostile to you. And that is where you live. That's where you live as a data processing system, and a data engineer. You have to build your system with this in mind, and monitoring is a key piece of this. Data will do things to you, here's a way to think of this. If data were a person, data would basically be like the worst person in the world. The most sadistic, imagine the most sadistic person who ever lived. Data is more sadistic. Data is more inventive. Data has nothing but time to make your life hell. Data will say things to you like this, oh, no, yeah, you've been processing this huge comma-separated value file that's like a couple trillion lines long over some distributed file system. Line 1,000,000,001 is going to be tab-separated because I want to keep it fresh, and that's how I roll on data. This is not a hypothetical example. This has happened to me. Or how about this? You're on the other end of things. It's like this rinky-dink little application that's literally it's the 12 employees at your little startup, and you're doing an address book for them, and somehow a 12-gigabyte video of their dog running in a field, base 64 encoded, has ended up in one of the lines. And Data's like, how's your buffers handle that? Are you enjoying that? Are you having a good time? This is, again, not hypothetical. This has happened to me. Or how about this? You know what's awesome? One birth date column in a file. You know what's even better? A second one. And what if we made it all null so that way we're all brothers and sisters and can sing happy birthday to each other every year on day null? That would be fantastic. Again, not hypothetical. Has happened to me. My absolute favorite one, the final one in this. This is recent, too. Ladies and gentlemen, I have looked into the soul of an EMR. That's an electronic medical record system, meaning this could be happening to you right now in your doctor's office. And the gender column had 3 possible values, male, female, or 1. So that in case you were a 1, you could go to your doctor and be like, I don't know whether I should buy Centrum optimized for men or women because I can't find Centrum optimized for men in the pharmacy. What do I do? And Data's like, deal with it. I don't live by your rules. This happened very recently to us. That's just mostly the easy stuff, by the way. Most of those examples were syntactic examples. They were errors in syntax, right? Stuff that was formed wrong. The last one kind of eases a little bit into semantics. It's the semantics that will really, really screw you up, and screw you up hard. For example, again, I wish this were hypothetical. Yesterday, a 1 in field 5 meant married. Today, says Data, I feel it more like it means smoker. Please tell me how you detect this. This is not easy to detect. This is not a syntactic error. This is the system upstream of you has changed its mind about what reality is and how it will reflect it. Oh my God, we're downstream of this. What do we do? Well, here's a couple things that we do. Number 1, we sample our data stream early and often. That is, we don't put some monitoring at the beginning of our pipeline and at the end of our pipeline. We are designing our pipeline in accordance with Matt Papi's principle number 1. We're making it a pipeline with discrete inputs and outputs, and we are sampling at every one of those points and figuring things out at every one of those points so that we're trying to keep errors and crap local. Number two, we are designing, I'm using the word customer here, substitute customer for the appropriate entity in your data processing system, but we're designing a fake customer, and we are constantly updating that customer. And here's what I mean. If you're doing analytics for a customer's web traffic, let's say, you're creating a customer that does not exist. You are feeding into every single run of your pipeline, every single one. You're feeding this fake data that you've created for this fake customer that you know how it's supposed to turn out at every step of your pipeline. You have done the, yes, I admit, painstaking and long process of figuring out, like, yes, there's 15 of these lines. 2 of them should be filtered out because of this. 3 of them should be collapsed into this, and so on. Therefore, this should be a that. And you are testing that your expectations are met at every single goddamn step of your pipeline. And you are very happy that you've had the opportunity to do this work, because otherwise, you don't know that your stuff is right. This lets you know a little bit, at least, that your stuff is right. And finally, you are leaning on volumetrics. Volumetrics, measuring the volume of something. How many things of X type versus Y type were there? This is a blunt, clumsy instrument that is the best we have in a lot of cases, the best tool we have to detect semantic changes, especially semantic changes. This is like your one hope with semantic changes. So the one where field 5 suddenly went from a 1 meant married yesterday, it means a smoker today. Presumably, there's some rough breakdown in your population of married versus single people, right? It's like, whatever, 70-30 is the one you're looking at or something. It varies a little run by run, but it's somewhere in there. If you are expressing in monitoring, you are monitoring the fact that you expect that breakdown to be about 70-30. And if it drifts too much one way or the other, you're blowing up and refusing to process another byte till someone takes a look. Now when it changes to smoker, and in today's day and age, there's no way 70% of your population's smokers, that's going to be totally off because you suddenly dropped it down to like 2%, and you have a chance. Volumetrics, this blunt, clumsy instrument, has given you a chance to detect a semantic change that otherwise you would have no chance to detect. Or another example. You've got a bunch of kind of CSVs representing tables from a database coming into your system. And there's like a foreign ID column that's linking up to another one. And they don't always all link up. Let's say most of the time, 90% of the IDs link up, right? So you're like, OK, I'm going to blow up if it's ever more than 95% or less than 85%, because it's usually about 90. And one day it drops to 4%. Almost none of the IDs link up. And your system blows up and tells you that this is the case. Fantastic. You have now just discovered this change in the meaning of your data before it was passed all the way through and corrupted and gave you the wrong answer, and you went out of business like Redacto Corp. In other words, it's not just invariance that you're testing and monitoring at every step. It's not just aggressive invariance that you're testing. It is aggressive, creative invariance. This requires the work of 3 sets of people to do this right. Now, sometimes these people overlap, but they have to have these 3 specialties in your company. Number 1, the data engineers, the people who are engineering this system, have to be involved in this and helping to think this way and understanding that this is valuable. Number 2, the people who know the data inside and out, the domain experts, the people who know the EMRs, they know the data warehouse you're reading from, they understand all that stuff, and they understand that this is a real job that must be done and is going to take time and thought. And the people who know your business, so that they understand we don't need to catch this kind of error because it's not expensive, but we do need to catch this kind of error because it's extremely expensive. Those 3 people need to be working kind of cheek and jowl all the time together to be coming up with aggressive, creative invariance that can be monitored at every step of your pipeline. And then you have some hope of surviving in your data processing system. This will consume lots of computing resources. Sometimes the steps that do the verification and the checks are the most expensive steps in your entire pipeline. The one that's gleaning the insight that like you're selling to other companies and making millions of dollars runs in 4 seconds. The one that's making sure that the data looks reasonable approximation of sane takes a day. That's awesome. Embrace that. Love it. That's good. That's a good use of computing time and human time as well. I will end with this principle, kind of a summation of this principle. In every single system where the 3 of us have ever introduced monitoring, where it did not exist before, in every single data processing system, now whether that data processing system belonged to us and was constructed by us, belonged to a customer, et cetera, we have found substantial errors, substantial problems. It is purely luck whether those substantial problems have fallen on things that were like Redacto Corp, that were super important to the business and drove them out of business or cost them a lot of money, or whether they happened to be trivial. But the problems themselves were of a substantial nature. There was a big error. I will sum up by saying I can come up with, it certainly can't be that every data pipeline has these, so I can only come to one possible conclusion, which is that monitoring creates errors. There's no other way that this could possibly happen, right? No. In fact, the errors are there. Monitoring is the only thing that's going to help you find them because of the opacity of a data processing system. So speaking of conclusions, final notes and parting exhortation. One thing has been kind of conspicuous by its absence from this talk, which is there's been no talk about like the big scaling data attack with the awesome sauce, Storm, Kafka, Hadoop awesomeness. That is by design, ladies and gentlemen, for two reasons. Number one is all these principles apply to those systems as well, and actually apply extra, because those systems tend to involve trade-offs that make these things harder to stick to and require extra investment to design systems along these lines. Number two is that this is a huge talk in and of itself. And I will say, if any of you are interested in that talk, let us know. We love to like come speak at local companies during lunch or whatever, and let us know. Hit us up afterwards. So let's just look at our 6 principles again. Think in pipelines. Data processing systems are born as scripts but must become software. Optimize mean time of change. Fail big wherever possible. Adopt a forensic mindset and monitor all the things. If you take these to heart and go home, think about them, look at your systems with those kind of in mind, I guarantee you more of you will find this enjoyable and be raising your hands when Sri asks you next year or a year after that. So thanks, go home, consider those, find some incremental ongoing improvements to make. Incremental is awesome at the beginning. You can buy a lot of win for a little investment if you're just getting started, and let us know how it goes. Thank you very much. So thanks. Let's do like one question, because then I want to make sure, Dan has an awesome talk that I want to make sure we have time for. Yes?
So we all love strings, but does it ever make sense to use things like force data not to misbehave?
Cool. The question is an awesome question. It is, we all love strings and text. Is there ever a time when it makes sense to not design your system around text and line-oriented formats, but instead to use something like protocol buffers or thrift, something that enforces a certain format kind of at the protocol level? The answer is yes, but I would put it in terms of costs. That is, it totally makes sense for Google, because Google is this massive company operating with many, many different departments operating on that data, and it's a big portion of kind of their operating expense is just moving that data around and so on. And they're typically doing things live rather than as kind of a data processing batch-oriented thing, so they can't rerun stuff. This goes back to Matt's point. And so I would say those are the kind of the first things that pop to mind that would go into that equation. So yes, not at all saying those are evil, saying that those have a place, the others have a place, and sometimes those overlap. Thanks a lot. Hands up.